I want to talk about the revolution that is taking place in statistics, where if I said to you, what is statistics? Is it formulas or is it understanding how to deal with complex distributions? So, reminding you of the first part of my talk, we talked about the 19th century formulas, paper and pencil solutions, heavy assumptions. And then we talked about the 20th century. And made the point that the 20th century concept is better pedagogy. So now let's cut to statistics. So what's the short history of statistics? Well, we have a real breaking point, and the breaking point is mid-20th century. And mid-20th century, why mid-20th century? The birth of modern computing. So in the 19th to mid-20th century, no computers, formulas, we get proof theorems, but it's tough to prove theorems. So we have to make crippling, trivializing assumptions that everything in sight is a normal distribution, and we're only going to talk about the means and standard deviations. So we learn about the t-test, where you calculate the t-statistic and you plug it into this formula and you see what the outcome of the formula is, or a chi-squared test. But all of these are derived for the means and standard deviations of normally distributed quantities. In the late 20th century, we see non-normal distributions where the median and the mean are very different. And we see bimodal distributions, which you should not even begin to apply these formulas to. It's absolutely wrong. It is malpractice to apply these tests to these distributions. They violate the assumptions. So what was the purpose of the formulas? The purpose of the formulas was to calculate something called statistical significance, or to calculate something called confidence intervals. So in this short talk, I'm only going to talk about statistical significance, but everything I'm saying is also true of confidence intervals. What is statistical significance? The thing that the formula gives you? It's an estimate of how unlikely your result is to have occurred at random. That's the thing called the p-value. So you calculate the t on your data and you plug it into the formula, and the formula tells you that if t is bigger than 1.98, then p is less than 0.05. What does that mean? P is less than 0.05 means the probability of your result happening by pure chance is less than 5%. How can we do that? Well, in the old way, we have to prove a theorem. In order to prove a theorem, we have to make heavy-duty assumptions. First, very heavy-duty assumption. Groups A and B have to be normally distributed. Second heavy assumption, you have to use the mean value to describe the groups. Third heavy assumption, you have to use subtraction to compare the two groups. If all of these things are true, I can prove it, or a student can prove a theorem that the quantity t will be distributed like a theoretical distribution called t of x, and then you compare your result to the tails of the t of x to judge statistical significance. What's wrong with this approach? It has produced an epidemic of irreproducible results and scandals. In this month, hormone replacement therapy causes cancer. Next month, hormone replacement therapy does not cause cancer. Aspirin prevents heart attacks. 6 months later, aspirin does not prevent heart attacks. How could so many studies be wrong? Because they relied on this concept of statistical significance. And this has now been identified at the highest levels as scientific irreproducibility, one of the big contributors is bad statistics. So as I said, what's wrong with the formulas is that the formulas are based on these heavy assumptions. Normal distributions as n approaches infinity, must use means and standard deviations. This is what we live with if we need to prove theorems. But these assumptions are absolutely crippling assumptions, even to our thought process. I saw this headline, average tax refunds up 40%. So I showed the headline to my class, and I said, based on this headline, which of the following is true? I can expect around $40 more. I can expect a bigger refund. Many people will get approximately $40 more. A typical refund will be $40 more. And E, none of the above. And of course, the correct answer is none of the above. I asked my class to do this. Here is the result. Here's the class poll. Only 22% gave the correct answer. 78% of the class gave totally wrong answers to this question. And when I showed this to them, they were all kind of crestfallen. And I said, why did you make this mistake? And the answer is because you bought something, you were conned into believing, and you bought the con that everything is normally distributed. Because if everything was normally distributed, these would all be true. But it isn't, and so it's not. So this assumption of the normal distribution in the face of data which is not a normal distribution is a major problem. The criticisms of the normal distribution that have now emerged scientifically are very, very decisive. They're very negative. People now talk about thick-tailed and long-tailed distributions, including sales at Amazon.com, songs at iTunes. The actual die-off here is much slower. It's a much longer and thicker tail than the normal distribution. So what's wrong with assuming a normal distribution model when you don't have a normal distribution? Well, one consequence is you get the stock market crash of 2008. How did that happen? Well, economists, mathematical economists, got the Nobel Prize in economics, which should be abolished. For the Black-Scholes equation, this is a differential equation that values the price of a derivative of an option. So one of the things that goes into the valuation of an option is how likely are big price fluctuations. If big price fluctuations are unlikely, then my option is more valuable. So built into the equation is this sigma, which they call volatility, but what it is the standard deviation of the price fluctuations. In other words, they're assuming that price fluctuations follow a normal distribution. Therefore, very little big deviations. But in a long tail, the number of large deviations is much, much higher, and you can't use formulas and t-tests. So if you estimate the likelihood of a catastrophic event is given by this, and the actual likelihood of a catastrophic event is given by this, you're going to make a very bad bet. And that's what everybody did. So just to keep on this theme, what do we suggest as an alternative to this mean value, the average, which is meaningful for normal distributions, but not otherwise? A very useful concept is the concept of the median. You rank your data, you find the midpoint, the 50th percentile, and that is the median household income, which is very different from the mean household income. These are quite different because these are not a normally distributed quantity. Not only that, the median gives you actual information, and the mean often does not. You saw how my students were actively misinformed by assuming the mean value is typical. For example, suppose you're a patient and you're told the average survival time with your type of cancer is 2 years. What can you assume? What's the take home for you? And the answer is, again, nothing. It's just like the tax return thing. What if 9 patients die within a month, but the 10th patient lives 20 years? Then the average survival time is 2 years. But that's not helpful to you. But if I tell you the median survival time is 2 years, now you have something you can use. You know that you have a 50-50 chance of making it to 2 years. That's a useful piece of information for your life planning. Why don't we use the median more? Because math professors can't prove theorems about the median. Because it's an if-then statement. It's not a form. There's no formula for the median. There's a procedure for calculating the median. But math professors can't prove theorems about the median. Therefore, you can't use the median because we can't prove theorems about it. Now, that's what we call backwards, I think. They're telling you what scientific measures you can and can't use based upon what they can prove theorems about. So I said the late 20th century was the big watershed, and this was the great paper that changed everything. Brad Efron is the chairman of statistics at Stanford. And look at the title of their article, Statistical Data Analysis in the Computer Age. So you ask, what were we doing before? And the answer is, most of our familiar statistical methods were designed to be implemented on mechanical calculators. Modern electronic computation has encouraged a host of new statistical methods that require fewer distributional assumptions. No more normal distribution assumption. And can be applied to more complicated statistical estimators. We welcome the mean and not just we welcome the median and not just the mean. What's the trick? Traditional methods of mathematical analysis are replaced by specially constructed computer algorithms. Basically, if you want to find out how often something happens, create the world, simulate the world, and see how often it happens. Excellent textbook by Friedman, Pisani, and Purvis makes the same point. In Pearson's time, 1920s, there were no computers to find the chances, so he developed a method for approximating the p-value by hand without having to do a computation that was, by the standard of his time, quite formidable. But by the standard of our time, you can do this on your phone. So why are we doing this? Why are we clinging to pre-computer methods to prove theorems which completely cripple our ability to describe the data? So let me just close by showing you what this would look like. So I have 2 groups, and I have a control group and a treatment group, and I'm looking at what the drug B did to the T cell counts in a Petri dish. And here is my data. So the first thing I do, which I can't do if I'm doing a t-test, is I have to look at the data and I have to say, what is the distribution? Oh, look, this is kind of skewed right. This is kind of skewed left. I can't use a t-test. Just t-test fail. So what can I do? Number one, I'm not committed to the means and the standard deviations and all of that. I have my group A and my group B. I plot them, plot their distributions. I look at them and I choose a group measure. Maybe this is the mean. Maybe this is the median. I then calculate my effect size, the observed result, which could be MA divided by MB divided by MA, could be MB minus MA. And I now have an effect size, delta obs. Next question is this difference, delta obs, large? After all, any two groups are going to differ on something by some degree. So the question is large relative to what? And the answer is large relative to what you might expect from pure randomness. So the question is, how big a difference would you expect to see if A and B were just two random samples from the same set? Now that's if A and B were normally distributed and you used a mean and this and that and this, then that question is answered by the T formula, which is unintelligible gobbledygook. And the student cannot possibly understand the gamma function, which is the infinite integral of beta. The message of the teacher is shut up to the student, is shut up and calculate. And I'm not comfortable with that. I don't think that's good teaching. I don't think that's a good understanding. So how do we answer the question? How big a difference would you expect? We take group A and group B and we combine them into a big box, forgetting where they came from. So now we just have a big pile of data. Then we do what's called resampling, or sometimes bootstrap. We take this big box of A and B combined and we sample a pseudo A and a pseudo B at random with replacement out of the big box. This is two random samplings from this distribution. Let's calculate the effect size there. Let's call that delta sub 1. Okay, that's one estimate. Let's repeat that 10,000 times. This is going to take 2 minutes on a laptop. Except if it's a fast laptop, in which case it takes about 30 seconds. So now we have 10,000 estimates of how big a difference would arise between these two groups using these measures if there were no difference, if we're just randomly sampling from the same universe. So we take our delta obs, your observed result, and we ask, where does it rank in the 10,000 simulated deltas? And if your actual delta is bigger than 95% of the simulated deltas, then your actual delta is significant at p less than 0.05, because it or results bigger than it occurred less than 5% of the time. And that's what p less than 0.05 means. So we make this histogram of the delta i's. Here is our delta obs, the actually observed result. In our randomized 10,000 randomized simulations, a difference this big never occurred. And so now we can say, result, the median T cell, we're using the medians here. The median T cell count was improved under the drug by approximately 10 cells per unit area, and P is less than 0.0001 because this never occurred once in 10,000 simulations. This is an understanding of statistics. If you want to see how often something occurs, set up your assumptions and simulate tens of thousands of times and see how often it occurred. So once again, we're in the same kind of situation. We have 19th century statistics with all of these crippling assumptions. And we have late 20th century statistics, which frees us freedom of measure, I like to say, measures other than the mean and standard deviation. All distributions are welcome. Skewed distributions, bimodal distributions, and we can accept them easily because we're going to randomize the world to create the test against which we're going to compare the actual data. We don't have to make crippling assumptions to derive gobbledygook formulas. The student comes to you and says, oh, I'm teaching the t-test. So you say, okay, calculate t. It's the difference of the means divided by the standard deviation and multiplied by the square root of n. And then plug this t into this formula for using the gamma function. And the student is saying, what is all this? What is this? And you have to just throw up your hands and say, sorry, I can't, I really can't explain this. So it's bad science. I've argued two things. It's bad science and it's bad teaching. And so the question is, why are we doing it? Thank you very much.